We live in this world that's powered by these impossibly tiny devices. But have you ever stopped to wonder how they're actually made? Well, today, we're going to go inside one of the most advanced factories on Earth to see how the very building blocks of our digital world are created. To get a sense of the scale we're dealing with here, just get this. A single smartphone can have over 90 billion transistors inside. That's more than 10 times the number of people on the entire planet, all crammed into a device that fits right in your pocket. I mean, it's a number it's almost impossible to wrap your head around.
So that's the big question, right? How is it even possible to build something on a nanoscopic scale inside these factories that are literally the size of cities? That's the huge paradox of modern engineering that we're about to unravel.
All right, so let's start our journey by zooming way, way in. We'll begin with a component you've definitely heard of, the Central Processing Unit, or CPU. The brain of your computer. And we're going to take a look at what's really inside.
You see, a microchip isn't some flat, two-dimensional circuit. No, you should think of it more like a complex 3D skyscraper. Right at the bottom, at the foundation, you've got billions of those transistors. And then stacked on top are over a dozen layers of super intricate wiring, all insulated from each other, connecting everything together.
And this is a great way to picture that wiring hierarchy. At the very bottom, you have the local interconnects. Think of these as tiny neighborhood streets, just moving data around a small little circuit block. Then, in the middle are the intermediate interconnects, which are like the main city roads connecting different sections of the processor. And then, way at the top, you have these massive global interconnects. They're the superhighways that zip data across the entire chip.
Okay, so let's look at that foundation of the whole microchip. We're going to dive into the absolutely mind-bending scale of the transistor itself, that fundamental little on-off switch that makes literally everything possible. So just how small are we talking? Well, a modern transistor can have features as tiny as 6 nanometers. Now, to put that into perspective, a single human hair is about 75,000 nanometers wide. You could fit over 12,000 of these transistors across the width of just one hair. It's just an unimaginable scale.
And to put it another way, a modern transistor is actually smaller than a mitochondrion, the tiny little powerhouse inside our own cells. And it's completely dwarfed by a single particle of dust. So this isn't just small. We're talking about engineering on a near atomic level.
Okay, so we know what we're building, but how in the world do you actually build it? Well, the manufacturing process is like an incredibly complex, high-stakes recipe.
I just love this analogy from the source material. It's like baking an 80-layer cake that takes 3 months to make and has nearly 1,000 steps in the recipe. The level of precision you need is absolute. If any single measurement, any temperature, or any timing is off by even the tiniest fraction, the entire batch, which is worth a fortune, is completely ruined.
And while there are almost 1,000 of those steps, they're all just variations of this core repeating cycle. It's a loop. First, you deposit a new layer of material. Then, you use a process called photolithography, which is basically using light to print a microscopic blueprint to create a stencil. That stencil lets you etch away a pattern, carving out the intricate circuits. And finally, you clean and inspect it before starting the whole cycle all over again for the next layer.
Okay, so we've been deep in the nanoscopic process. Now let's zoom out. Let's pull way, way back and look at the place where it all happens. We're going inside the mega factory, or fab as they call it, a place of just incredible scale and cleanliness.
These facilities are gigantic. The clean room alone can be the size of 8 football fields, and it is filled with hundreds of machines, some as large as a city bus, each costing millions, or in the case of the really advanced lithography tools, hundreds of millions of dollars.
So how do you move these super delicate silicon wafers between hundreds of machines without a single speck of dust messing them up? The answer is these things, front-opening universal pods, or FOUPs. They're these sealed robotic containers that shuttle stacks of 25 wafers around through an overhead transport system, totally isolated from the outside world. It's pretty cool.
So those hundreds of tools on the factory floor, they all pretty much fall into these core groups. You've got lithography tools to create the stencils, deposition tools to add material, etchers to remove it, ion implanters which modify the silicon by precisely shooting atoms into it, and of course a whole bunch of washers and metrology tools that are constantly cleaning and inspecting the wafers.
So we've seen the micro, and we've seen the macro. Now, let's bring it all together and actually follow the journey of a single piece of silicon from just a blank disk to the finished processor that powers your computer. The whole process starts with this, a 300mm ultra-pure silicon wafer. Now, it's an amazing piece of engineering on its own, for sure, but at this stage, it's only worth about $100.
But fast forward 3 months and nearly 1,000 manufacturing steps later, and that same wafer is now worth closer to $100,000. That immense value comes from patterning billions and billions of transistors onto its surface. It actually becomes more than 10 times more valuable than its weight in solid gold.
But of course, not every single chip on that wafer comes out perfect. A single microscopic defect can disable an entire section. And this is where a really clever process called binning comes in. The chips are all rigorously tested, and based on which parts are fully functional, they get sorted into different product categories. So a chip that was supposed to be a top-of-the-line i9 might get sold as an i7 or an i5 if some of its cores are faulty. It's a brilliant way to maximize how many chips you get and minimize waste.
So after all that testing and binning, the wafer is cut up into individual chips. Each of those working chips is then packaged up, mounted on a little circuit board, and topped with a metal heat spreader, which makes it ready to be installed in a device.
So the really crucial thing to take away from all this is simple. Everything you do online, every photo you take, every message you send, it's all made possible by this incredible, incredible process. Our entire digital civilization is built on this foundation of engineering at a scale that is just almost impossible to truly imagine.
And that leads us to a final, really fascinating question. For decades, all our progress has been defined by making these transistors smaller and smaller and smaller. But we are rapidly approaching the actual physical limits of atoms. This process powers our entire world, so what happens when we just can't shrink it any further? Well, that's a question engineers are racing to answer right now.